All right, welcome. We're taking a look at chapter 4.4, the mean value theorem. All right, and when we're talking about the word mean in this situation, we are not talking about something that is an angry value theorem. No, we're talking about mean as in the average. All right, the average value of a function. Okay, so if we have let me just state this. This one is not as useful for us to actually do things. Okay, let me just be honest about that one. Not a super useful function or theorem for us when we're just calculating things. Okay, but what it is really useful for us is when we start to, truly look at the math behind how to calculate derivatives in calculus 1 and these things called integrals in calculus 2. It winds up being really useful to connect those two things. We don't really go into super great detail, but if you were taking more of a rigorous course on like why calculus works, called real analysis, this is very, very important. So we're just going to get kind of the basic introduction. All right, so the mean value theorem says if you have a continuous function, okay, over some interval, and you can take the derivative on that interval, okay, not at the endpoints, of course, but just in the middle. Okay, so you have a function. If you can take the derivative of the function every single place, okay, then there exists some point, okay, at least one point, could be multiple points, where the derivative of your function is equal to just the overall slope of this function on this interval. All right, so what this means, if we start here and we stop here, if we connect those 2 points, we have a slope, right? All right, way back when, secant lines, we can calculate this slope. Kind of cuts out all the in-between stuff. Excuse me. All right, so the mean value theorem just says somewhere in between here and here, your function will have the same slope as just the line from here to here. So notice this spot right here and this spot right here. Those two spots, their tangent lines, would have the same slope overall as this entire function. Okay. There is guaranteed to be at least one spot where this happens. There might be more, but the slope of a tangent line will be equal to the slope of the overall secant line, at least somewhere. Okay. And that is what the mean value theorem says. All right. So let's just see if we can do this. Let's put it together. All right. Let's say we have f of x equals x squared plus 4x minus 5 over this interval. All right, so let's give it a graph. Oh, excuse me. I'm sorry. All right, we just care about the interval from -4 to 2. All right, so -4, 5, -3, 2, -2, 1, -1, 2, 0, 5, 1, 10. Well, that was a terrible choice. 217 way up here. Did I type that in wrong? I think I must have typed that in wrong. I did. I was like, I wouldn't have made that big of a mistake making this graph. All right, let's try that again. All right, we've got -4, -5. I just need to erase all this, don't I? All right, let's try that once more. -5, -4, -5. I promise I can graph. -3, -8. -2, -9, -8, 0, -5, 1, 0, and 2, 7. All right, that looks better. All right, so we have this function. Now, we are stopping the function. We're not going past those two things. All right, can you find the secant line, the slope of the secant line? Well, to find the slope of the secant line, we do f of 2 minus f of -4 over 2 minus -4. The value of the function at 2 was 7. The value of the function at -4 was -5. Minus negative turns to positive. So we overall have 12 over 6, or 2. Okay, the idea is if you connect from here to here, it'd be like going up 2 over 1, up 2 over 1. So if you just went the straight line and not follow the curve, it would have the slope of 2. Okay, so the mean value theorem says somewhere on this function, this graph will have the slope of 2. Okay, if the overall slope between these 2 points is 2, somewhere in here you'll have a slope of positive 2. Okay, so for instance, our slope here is negative. All right, from here to here, the graph's going down, our slope is negative. Here, the slope is 0. All right, so it went from negative to 0, and then the slope starts to get positive. So somewhere along the line, we're going to have a slope of positive 2. Question is where? All right, so to do this, you take the derivative. Right? You then set the derivative equal to what we need it to be. Subtract the 4, divide by 2. Well, and we have our answer. When x is -1, our slope right here is 2. Okay, so when x is -1, we have the same slope as the overall secant line. Okay, that is what the mean value theorem says. Somewhere on this function, when x is -1, we'll have the same slope as if you just connect these two spots. Okay, now again, this is going to be useful if you are trying to prove the theorems of calculus. For us right now, it doesn't seem to really make all that much sense. All right, it's just kind of there. All right, so let's maybe try this one. We got the square root of x from 0 to 9. I can do that one. All right, 0, 0, 1, 1, 4, 2, 9, 3. All right. So if we just look at the interval 0 to 9, and you find the slope here, f of 9 minus f of 0 over 9 minus 0. So we have 3 minus 0 over 9 minus 0. That is 1/3. All right, take our g prime. Remember, x to the 1/2 is the same as the square root. So move that exponent in front, subtract by 1 to do our derivative. Move that negative exponent to the bottom, turn it back into a square root, and we've got our function. We want the slope, the derivative, to be equal to the overall slope of 1/3. So we want to solve this equation. Well, when you have fractions equal fractions, we can cross multiply. We can divide by 2. And then we can square both sides. So we get 9/4, 2.25. So right here, we will have the same slope. This tangent line will be the same as the tangent line, or the secant line, of just connecting those two spots. All right, they would be parallel. All right, that is the general idea and what we're finding. All right, again, overall, not super useful for us, but there is one decent use. This idea, you pass a traffic camera at 10:05 a.m., you're going 55 miles per hour. Okay, 36 minutes later, you've gone 39 miles down the road, and you pass another camera. Okay, again, you're going 55. That's great. Okay, the speed limit's 60, so you're not even speeding. But for some reason, you got a speeding ticket. That seems a little strange. You're going 55 when you pass the camera. You're going 55 when you pass the camera. Why would they send you a speeding ticket? Well, the idea is, yeah, you're going 55 when you pass the camera. Maybe you knew that camera was there. All right, you're going 55 when you pass the second camera. But in 36 minutes, you went 39 miles. Okay? So that means if you take your total distance divided by the total time, you were going 1.083 miles per minute. Now, to change this to miles per hour, we times by 60. And what that means is that at some point in time, okay, well, to say this the right way, you averaged 65 miles per hour. Okay, if we're here at 10:05 and 36 minutes later, you've gone 39 miles. Yeah, you slowed back down, but your average speed, your mean speed, was 65 miles per hour. Yeah, you slowed down when you passed the cameras, but your average speed, not just at one moment in time, but your average speed was 65 over the speed limit. Well, if your average is 65 over the speed limit, yeah, you deserve a ticket. All right. You slowed down for the cameras, but your average was 65, which means you probably were going over 65 at some point in time. I can't prove that, but you likely were. I know you averaged 65 for that entire journey. Okay, you went above the speed limit, no doubt about it, and your average is above the speed limit. So that is just one little idea there, something that we can work with. So given this equation represents the height of a ball dropped from a house, we can find when it would hit the ground. You just set the equation, the height equal to 0. Move the 20. Divide by negative 16. That'll change to positives. And then we take the square root. So the square root of 20 over 16. So that'd be what? The square root of 20 over 4. Let's just go ahead and type that in. So it's going to take about 1.118 seconds. All right, so let's find the ball's average velocity. Okay, we dropped it. It landed in 1.118 seconds. So let's find its average speed. Okay, so what we can do, we know the height at 0 seconds and then 1.118 seconds. That was the time the ball was in the air. Well, its height at 0, if I plug in 0, 0 squared would be 20. If I plug in 1.118, I'm going to get 0. So the measure of the secant, or the slope of the secant line, would be the average velocity, all right, from when we start to when we finish. So our second y value minus our first y value over our second x value minus our first x value. So we wind up with negative 20 over 1.118. So our average speed was negative because the ball was dropping, 17.889 feet per second. Right? So we drop about 17, 18 feet every second. It took just over 1 second to hit the ground, so that should hopefully make sense. So at what time was the ball's instantaneous velocity equal to its average velocity? Well, the instantaneous velocity is the derivative. Right? So 2 times negative 16, negative 30, derivative of 20 is 0. We then set this equal to our average velocity. We would divide by 32. And this would be at about 0.559 seconds in. So pretty close to about halfway into the drop, we've reached our average velocity. All right, the instantaneous and the average are equal about halfway down the drop. All right, one other fun theorem that we have is Rolle's theorem. All right, it states that every continuous and differentiable function f of x, if the two endpoints of your bounds are equal, then at some point in time in between the two of them, you have to have an extreme value. Okay, so if I know I'm at this height here, and I know I'm at that same height somewhere else down the line, somewhere in the middle, my slope had to be 0. I had to have an extreme value. All right, so if these two spots are equal and they get connected, and the function is continuous and differentiable, to get from here to here, if I go down and then back up, at some point in time, my derivative is equal to 0. There has to be some extreme value. There could be more. All right, this one has 2 extreme values in the middle. But if those two are equal, somewhere in time, I have to have a slope of 0. Now, it might be here to here, the entire thing is a slope of 0. That's fine. Everywhere has a slope of 0. All right, but more than likely, it's just at one spot or maybe 2 spots. Right? So use the table of values for this thing to show that there must be some form of an extreme value. So we've got x cubed minus plus it's x squared plus 2x plus 1. All right, so I'm not going to hit the graph button. I'm just going to look at my table. I've got 16, 25, 22, 13, 4, 1, 10, 37. All right, so we're at 16. We go up to 25, back down to 22, down to 13. Well, somewhere between here and here, our two functions were equal. All right, we started at 16. We went up to 25, back down to 13, down to 4, down to 1, but then back up to 10 and 37. All right. So I know I've got to have an extreme value somewhere in there, and I know I have to have an extreme value somewhere in here. All right. So I know somewhere between -5 and -2, and between -2 and 30 and +2, I've also got to have another extreme value. I guess I could even say somewhere in between -1 and 10. Not -1, 10, -1, and +1. I've got another extreme value. Okay, so I can say these two and those two. Okay, I can't say between -5 and -3, because if I start here, I've got to get past 16 again to show that those two at some point were equal. Okay, so our graph should agree with us here. Well, that's terrible. Let's see, -6 to 3, -5 to 4. All right, so somewhere between -5 and -1, -2, and -2, I had to have an extreme value, and somewhere between -1 and +1, we had to have that extreme value. Okay, so that's just the idea of Rolle's theorem. All right, somewhere in between those two spots, you have to have a zero slope. Okay. I used to coach basketball, so I thought this would be a decent idea. If I run it down and back, so I start on one end of the court, I run to the other, I then turn around and come back. 90 feet down, 90 feet back. I do this in 12 seconds. Okay. So what is my average velocity in feet per second? Okay. So I ran 90 and 90. Divide that by 12. So 180 divided by 12. Would be 15 feet per second. All right, does that mean I ran 15 feet per second the entire time? Well, no. I start at zero, a speed of 0. I increase, then I slow down so I can stop. I actually have a speed of 0 for a second, and then I increase, and then I slow down again. Okay. So the general idea is that at some point, yeah, I was running 15 feet per second, right? Probably somewhere here in the middle. Actually, probably closer to the two ends. I probably wound up going really fast, more than 15 feet per second here in the middle, because I slow down to a speed of 0, and then I speed back up and slow down to a speed of 0 again. Okay. So the Rolle's theorem tells me that at some point in time, if I start here and end here at this same spot, somewhere in time I had to have a slope of 0, a speed of 0. I had to stop sooner or later in order to go down and back. Sooner or later, I had to be a speed of 0. Okay. All right. So that's Rolle's theorem and the mean value theorem. Again, they are useful further down the line. They're not all that useful for us right now, but hopefully they will be at some point.